In this tutorial we will use ROS2, Sim and LeRobot to do push-T simulation. We will create a model using Sim, operate the robotic arm using joypad and collect data using ROS2. Then, we will train diffusion policy using the LeRobot library and execute trained model. First of all, we need to install required tools and libraries. In this tutorial I expect that the viewer has already installed ROS2 Humble. If you have not, please follow instructions on this page and install it. Next, install Sim. We should follow the procedures described in this page. Create a new virtual environment. Activate it. Install Sim using pip. Install TypeGuard. This library provides runtime type checking for functions defined with PEP 484 argument. We will install LeRobot into the same virtual environment. Installation procedure as described at LeRobot GitHub page. We just have to clone this repository. In the virtual environment we have just created, move to LeRobot directory. And execute this command. If you encounter this error, install these packages. It seems that we have to change Python dev to Python 3 dev. How to train our own policy is described in this section. It is simple. In case of training push-T environment with diffusion policy we just have to execute the 3 train policy Python script. After execution of this script, training data will be downloaded. The training data is stored in the cache directory. So, to train our own model, we have to create a dataset with identical data structure. LeRobot dataset data structure is explained in the LeRobot dataset Python script. It consists of 3 major directories: data, meta and videos. Data directory contains set of Parquet files. Parquet is an open-source, column-oriented data file format designed for efficient data storage and retrieval. Let's see what we have inside the Parquet file. Please download the UR5 simulation zip file and extract it to your home directory. We can print data using the show data Python script. This is a very simple script. We just read the Parquet file using the read Parquet function of the pandas library. We have 10 columns of data. The meaning of each column is described at Gimpush GitHub page. But it seems that LeRobot dataset does not strictly follow these definitions. For example, according to Gim definition, observation space should be 5 or 16 dimensional, but here we have only 2. We will reproduce data following LeRobot dataset. In the meta directory we have various definitions and statistics data. In the tasks.json lines file, task instruction and task index are defined. We will leave this file as it is. In the info.json file, we have definition and information of the dataset. In our case, we will change these parameters and shape of an image according to our image size. In the episode states.json lines file we have minimum, maximum, mean, standard deviation and cout values for each parameter. Since these values are unique for each dataset, we will regenerate this whole file. In the episode.json lines file we define episode index, task instruction and length of each episode. We will regenerate this file as well. Now we are going to create a simulation model in Isaac Sim. Open Isaac Sim. Import the URDF file of the robot. Create ground plane. Basically, we are using the URDF file of UR5 robotic arm from this repository. But initial angles in the URDF file have been changed so that the robot will be able to do the push T task right after the simulation starts. Also, robot stand and tool to push T bar has been added to the URDF file. We will use MoveIt servo to operate the robot, but we will not go through setting up process in this tutorial. Please see these tutorials for that. To enable operation of the robot, add articulation route to the world link of the robot. Also, increase max force and stiffness parameters of each joint. Import the simple table URDF file and move it forward. On the top surface of the table, shape of T-bar is drawn. To create a URDF file with texture, please see this tutorial. Import the T-bar. Under the Links menu, select Movable Base. And under Collider Type, select Convex Decomposition. Move the T-bar on top of the table. Note that we set initial position of the T-bar a little bit above the table. This is because it seems that sometimes physics cannot solve contact constraints when relative velocity of two bodies is zero in the very beginning of the simulation. Also, in the physics scene we increase time steps per second value. This also helps to calculate contact correctly. But increasing this value too much will cause negative effect on frame rate. Select the T-bar and right-click on it. Select Add, Physics, Colliders preset. Add Collision preset to the RIST-3 link too. To control the robotic arm, we have to create articulation graph. Add these nodes to the window and connect them. we will subscribe to the joint states topic. In the articulation controller, select World Link as a target prim. This robot has two cameras. The first one takes picture of the whole tabletop. To add a camera, select Camera from the Create tab. Move it above the table. The second camera is attached to ROS2 link. So, create another camera and move it into the ROS2 link. Note that we don't need any joints to connect camera to the link. We can check camera image from this icon. Now we need to add ROS2 OmniGraph to publish camera images. Click on Tools tab. Select Robotics, ROS2 OmniGraph, Camera. As a camera prim, add top camera. Because we don't need depth images, uncheck depth and click OK. Add wrist camera the same way. We also have to collect position of end effector, that is tool, and position of T-bar. To do this, create a TF publisher graph. As a target prim, add tool and T-bar. To define simulate friction between objects, we have to create physics material. Select World, Create, Physics Material. Check Rigid Body Material and click OK. Add these values as extra properties. Now select the T-bar. Select collisions of the T-bar and add this material in the Physics Materials on Selected Models section. Also, under Collider menu, as an approximation method, select Convex Decomposition. Do the same operation for the tool as well. Now, our Isaac Sim model is ready. Let's see the ROS2 part. Open the data collection Python script. We have multiple subscribers which subscribe to TF data, Joy topic and camera images respectively. All this data is utilized in the data recorder class. In the Get Poses subscriber, we obtain position of the tool and the T-bar. Note that we use rotation class of SciPy library to convert quaternions to Euler angles. In the Joy subscriber class we convert input of the left stick of PS4 controller to action. Data recording starts when the X button is pushed. If we push the X button again, recording will stop. Note that a small delay is added to avoid chattering. In the wrist camera subscriber and the top camera subscriber, we obtain an image and resize it to half size. These images can be used for training, but we are not using them this time. In the data recorder, we create necessary directories, read images for drawing and constants. Here we also define data frame. Obtained data will be stored in the according column each time step. An important thing is that each new episode, we have to set index and episode index as written in the comment. Otherwise, there will be an error in the training script. In the timer callback function, we draw an image of the top plane of the stage, tool and the T-bar. This image will be used in actual training. Note that data recording will automatically end if we reach success state, that is if T-bar region will be covered more than 90%. When data recording is done, a MP4 file and a Parquet file are generated in the specified directory. Now we are ready to collect the data. Firstly, execute the -build command. Then, launch Isaac Sim. Launch the ARM Joy Control Launch Python script. Finally, run the data collection Python script. To avoid necessity of executing -build command after changing index and episode index after each episode, run the data collection script using Python 3 command. By operating the left joystick of the controller, move the T-bar above the blue T-bar image. Collect as many episodes as possible. After data collection, create a directory with the directory structure required by LeRobot and move collected data there. Then, execute the create episodes JSON-L Python script in the create episodes stats JSON-L Python script. Move generated files to the meta directory. Collecting data requires time and a little bit of skill in robotic arm operation. So, in this tutorial I provide a folder with data and generated JSON files. You can use them for training. Please move this folder to your home directory. To run the training, move these two scripts into the LeRobot examples directory. These scripts are modified versions of original scripts included in this directory. To execute training, run the 3train policy mod Python script. Trained model will be stored under my push-t diffusion directory. For policy evaluation, we will use this to evaluate pre-trained policy ROS Python script. Here, make sure that you have specified correct directory. To execute learned policy, open the Isaac Sim model we created. Then launch the ARM diffusion control launch Python script. Finally execute the to evaluate pre-trained policy ROS Python script.